IPv6 addresses are kind of like family. Some of them are normal, some of them are a bit strange. By the time we're done here, we will examine the 5 types of IPv6 addresses and see how they are used. So what I'd like to do is kind of pick up where we left off in the previous nugget. I had set up one of our routers, actually our Arizona router, this guy right here, with a loopback IP address. And the primary reason I did that was to essentially show you how we can shorten the address, because the Cisco router does it for us. Then we can talk about the rules on how we did that. But one of the things you might have seen in the output from the show command was there was all these other addresses that just showed up out of the blue. What are those doing there? That's one of the biggest things to get used to when you get into the realm of IPv6. Hang on, let me shrink my window a little bit here. Is that you're not just dealing with one address anymore, you're dealing with multiple. So I'm going to do a show IP interface brief, right? My favorite all-time command in Cisco. Notice, first off, that this shows the IPv4 address because we said IP. In just about every command, they have a v6 variant. So we can type in IPv6 interface brief, and we see the address that I typed in right there as one of the addresses that are listed on that loopback interface, and automatically it generated this one right here. And hang on, what's more than that? Let's do the full output, show IPv6 interface, and I'll just do loopback 0. So we just zone, that's the only one that has an IPv6 address. So I see not only a global unicast address right there, I see a link local address, whoop, right there. I see group addresses, whoop, right there, and there, right? So we've got all these addresses that just showed up even though I only configured one of them. So what's the deal? Well, truth be told, there are actually 5 different types of addresses in the IPv6 world. Some of them are known and visible. Some of them are a little unvisible. Did I say unvisible? Invisible. You know what I meant, right? So first off, we have the unspecified address. I'd love to go top to bottom because it just is logical. Unspecified is essentially, I don't have an IP address. That works really well for a DHCP client that's pretty much screaming, help, I need an address, and it sends out that IPv6, we'll say broadcast, but there is no such thing in the IPv6 world. There's only multicast messages. So what you'll see is a computer without an IP address send it to a destination of a multicast, and the source address will be ::/128. That's essentially saying I don't have one. So you might say, well, if this computer's connected right here and it's sending out that multicast message with no source, how does the remote device know how to get back? Well, remember, IPv6 is a layer what? Layer 3 address, right? In that same header will be the layer 2 information, which is going to be the MAC address. So when it is received, let's say this guy is the DHCP server, because we have those in IPv6, it's going to be able to see the source MAC address of this guy, and since we're in a switched network, it'll work just fine to reach it. Now, right below that is a loopback address. And if we look at that in binary terms, it's essentially 127 zeros and one at the end. That's one of the interesting things that they did when they moved from IPv4 to IPv6. Do you guys know what the loopback addresses in IPv4 was? You remember that? It was 127 dot anything. It's technically called a Class A address, but some people will say, it's not a Class A, it's a loopback. So the most famous address in the world is 127.0.0.1 because that's essentially, out of that whole Class A range, the only address that they used. So somebody wasted, 4 million some addresses. It's probably Harvey, who doesn't work there anymore, who was like, that's a great idea because we could use it for something. And they ended up using one address. Well, they fixed that in IPv6 because they made the loopback just one address. So you will see, well, this is one of the invisible ones. You will not see, but you can actually ping on any device, ::1, which is all zeros, 1. That's the subnet mask, which is essentially all ones. And it will actually ping the local device. Now, loopbacks are useful for more than just pinging yourself, because that's kind of odd. That's not very fun. You can actually access applications, server applications running on your own computer or server as a test case. So the loopback it actually can be really useful. So knowing that that's there is really handy. So now let's get down to the real ones. And these are the ones that we did see. We actually saw those in the show output. The first one is the global. Now, I'm going to roughly say this. Don't quote me on this. Somebody would say, he's wrong, because I am. But I would essentially equivalate, I love making up words, this to public IP addresses, right? So when we're on the internet as we know it, not the Metro E, the internet, up here in the IPv4 world, we're used to seeing addresses like 200.1.1, and people immediately recognize, hey, that's a public IP address. Why? Because it's not 10. something or 192.168. It's a public internet IP address. Well, in the same way, they said, we're going to define a global range of addresses in the IPv6 world, and these will act as the internet valid IP addresses, the things that will work on the internet. So that's why I'm saying you could call them public IP addresses, but they limited it down. I mean, think about how many cajillions, I can't even say the word, it's a word that I don't know, how many cajillions of IP addresses they have. Well, they said, let's start small here. I mean, we can address the entire planet for years and years to come. If we just block off the first 3 bits, we will say in binary, the first 3 bits of these global addresses will be 0, 0, 1. Now remember, hang on, I spent a lot of time on this with you. Remember when we look at an IPv6 address, right? You've got 128 bits, but we don't look at it like that. We look at them in nibbles. So if you look at those first 4 binary bits, I would say the first nibble, right? They're saying it has to be 001 X, and then you can have whatever you want after that. So what that says, again, convert that to we'll call it a hexadecimal number or a decimal number. We would have the first digit of our IPv6 address being 2 or 3. Now, why is that? Well, remember, again, and I do, guys, I do this for me because I know it's one of those things that just takes time to get used to. In the IPv6 world, every 4 binary bits is just a single character. Remember, we've got that IPv6 address that might be something like 2001:111, this whole big long thing. And when I'm saying the first 3 bits have to be 001, I'm just talking about this first character because it takes 4 bits to make that first character, right? So look at what I'm saying here is if we're looking at it in hexadecimal, that means it will be some number from 2000 through 3FFF. Because again, if we just reserve those first 3 bits and we say it has to be 001, that's the public IP addresses that will encompass the entire world and save us for my lifetime, your lifetime, and our children's lifetime to come, because there will be that many addresses available, then what that means is that first nibble or that first character in the IPv6 address could be a 2, because it could be 0010, right? Which would mean it's a 2. Or it could be a 3, because we could have 0011, right? Because we've only said the first 3 bits of that nibble must be 001. So 2 or 3, that's why we got this range. And remember, this is just the first hextet. So let me just say it in plain English. What I'm trying to say is the future internet, some people call it the Internet 2, will have public IP addresses in use where the first hextet is some value from 2000 through 3FFF. Now, keep in mind, the Internet 2 is alive and well. And most of the time what you'll see out there, if you when you get into BGP, you might just Google. It's kind of fun. Go to Google, type in BGP IPv6 routing table. There's actually sites that will let you see. They call them BGP looking glasses. If it's Friday night, I'm giving you like don't rent a movie. Don't rent a movie. So worthless. Go to Google BGP IPv6 looking glass, or some variant thereof. And it will actually show you the IPv6 internet table, the internet routing table of the Internet 2. And you'll see that most of the addresses out there today start with 2001. That's just because 2000 seemed too, I don't know, epic, too foundational. You'll see some 2000 addresses out there, but that's why in all the examples that you see, most of the addresses that I use are all 2001 : something. That's because today, most people are using that. Now, let's talk about the multicast address. Just a little refresher. We had that show IPv6 interface, and we saw that this interface had joined the group addresses this, and this. those are different multicast address groups. So here's the idea. In IPv6, they said, let's get rid of broadcast. There will be no broadcast anymore. And what that means is you won't have a computer that's able to just start sending random messages that everybody on that network receives. Although, when you look at some of the multicast groups that they create, some of the multicast groups are essentially everybody in the network. So in a way, they're like, there's no such thing as a broadcast anymore. But we have a multicast that does pretty much the same thing. So when your computer or your router or your switch or your whatever you plug into the network gets an IPv6 address, it will start joining multicast groups. Now, what multicast groups it's going to join will really be dependent on what kind of device it is and what features you're turning on. Like if you're turning on routing protocols on your routers where all the routers talk together, they'll start automatically joining groups that allow those routers to communicate using that routing protocol. At this stage, the only thing that you'll want to know is that the multicast address will have the first 8 digits, or essentially the first 2 nibbles, or another way, the first 2 characters in hex as all ones. Thus, you can see FF, and then I put 00. It doesn't have to be 00. It could be something else. But essentially, if you see something starting with FF, bam, dead giveaway, you've got yourself a multicast address. And remember, a multicast address is one too many. That's the beauty of it, is these work kind of like radio stations. If I'm joining the multicast group, let's just say FF00::1, for example. That means I have joined that radio station. I am now going to receive communication that is being sent to that frequency. If I send a message to that frequency, then everybody else that is joined to that multicast group will receive that message as well. So sometimes people say, well, multicast is where you can share an IP address. And I'm like, kind of. I mean, I guess you could think of it that way. It's the same address assigned to multiple devices, but it's more of like a radio frequency that feels better to me, because then you don't run into that, well, what about a duplicate IP address? That's not what we're talking here. It's one address group that multiple devices join. Now, the beauty of a multicast group is you can extend that beyond the LAN. For instance, I'll give you one use, and then I'll be done with multicast. You could have a video streaming server that you plug into this network, and let's just say it's streaming music for your voice over IP system. Well, you can actually have that streamed via multicast where it goes through the entire system and is sending that music all the time to all the different offices. So it's one single, and of course I just messed it up right there. It's one single stream that actually reaches all offices rather than having to send individual streams for every single person that puts somebody on hold. So that would be streamed. That's why I call it like a radio station, maybe FF00::, we'll just say 50, right? And so all of the devices, which could be IP phones that need music on hold, when you push the hold button, they automatically tune in to that address, and they're going to hear the music that's being streamed from that server at any time. It's kind of cool, right? So last type of address, and this is the weird family member. It's the link local address. So somebody decided that every IPv6 device would have an address to be able to communicate on the local network, even if nothing was handing out addresses. Now, one of the things that you'll find as we get deeper into IPv6 is that there's many ways of handing out IP addresses. There's DHCP, just like the old ways. You can have them auto-generate to where these guys figure out what address they have by discovering what the network prefix. I mean, I don't even want to get into that. There's all kinds of different ways they can get addresses. Well, let's just say all of those ways break down. Every device that is IPv6 standards compliant will automatically generate its own link local address. The reason I say this one's weird is because of how they decided to generate it. First off, this part isn't very weird. They said the first 10 bits of a link local address in binary will be you can see it right there, which in hexadecimal ends up being FE80. That should be like a ding, 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 radar. If you see FE80, you've got yourself a link local address. And let's go back to my router. It logged me out. I'll get logged in there. Show IPv6 interface loopback 0, right? Right there, boom, FE80. I immediately know that I have a link local address. Then look at this. We've got this : and then this mishmash right here. This is an auto-generated address which applies or adheres to the rules, jot this down, known as EUI-64. So they were like, okay, how do we have computers figure out a random address that they could be and it be unique in the world? Here's what they did. They said, let's take that computer's MAC address, right? And you guys know what a MAC address is, right? It's burned into the network card, the MAC address. And let's just say this is 1111.2222. I'm just making up a MAC address just for grins, right? So we're going to take that. And by the way, a MAC address is 48 bits long, also hexadecimal. So you got a 48-bit address, but it's called EUI. Wait a sec, we're missing some bits, right? So what they do is they say, okay, let's take that. That's our step one. Take the MAC address. Step two is let's split it right down the middle. So we'll have 111.122 break 22.3333. Right? I guess I could start taking the dots out of there. So it splits it right down the middle because they realize, wait a second, we only have 48 bits. We have to add 16 more in order to get to our 64 bits that's required for EUI 64. So, okay, step three, what do? We say, okay, take that MAC address, that's right here, and squeeze in the middle, FFFE. It's the weird family member, right? Why did they do that? I know somewhat, you're like, why would you do that? I don't know, because they're like, this would be too easy otherwise. Salaries of network engineers would go down because everybody could get it if we didn't do something really whacked. But wait, there's more. It gets crazier, right? So they squeeze that in. So now you've got this MAC address that's, okay, 1111.22 FFFE 223333, right? Okay, good. So we've got that. And then step four, they're like, let's just flip a bit. What'd you say, Jeremy? What? No, flip a bit, B-I-T, right? So what they said is we're going to invert the 7th bit. And you're like, what are we doing here? Well, let me show you exactly what that means. And now you're gonna get it. You're gonna go, that's why he wanted me to convert from hex to binary. So this kind of stuff makes sense. let me rephrase that. Doesn't make sense. I can at least figure out how to do it, right? I still don't know why they did this. So remember, each one of these is a nibble, right? In binary. So we've got 0001 would be that first one if we're breaking back in binary, right? How many bits is that? 1, 2, 3, 4. Okay, and then this one 0001. Okay, that's 5, 6, 7, 8. That would be the second one. But I said, the 7th step of the process is we just flip a bit. So 7 bits in, 1, 2, 3, 4, 5, 6, 7. You flip it to from whatever it is. So it was a 0, it will now be a 1, right? So when you're looking at the link local address, while the split and the weird FFFE in the middle was weird enough, they said let's just change that 7th bit, if you will, to where now it would be 1, and what would that be in binary? That'd be 3, right? 3 1 1 2 2 FFFE 2 2 3 3 3 3, because that's good. And then by the way, this whole thing that I'm talking about is the last 64-bit. So let me put both of these puzzle pieces together. You're then going to take this beginning FF. Oh, wait a sec. Not that. FE, I'm thinking multicast, FE80 colon, put that right in there. 1311 colon 22FF colon FE22 colon 3333 /64. Remember, our shortening rules means those represent consecutive groups of zeros. So technically, that would be 3 consecutive groups of zeros represented. Because remember, IPv6 address, 8 hextets, right? There's 1, 2, 3, 4, 5, 6, 7, 8 hextets. That is your link local address. Are you still with me? Did you fall over? Please. Remote CPR. It's like, it's like, what? So why do I care? Would be the question I would be asking right now. I mean, it's this strange auto-generated address. What for? Well, first off, if you're studying for certification exams, let me just say, if I was a test writer and I'm like, I just want to be mean, which a lot of them are, I would just be like, let's just be like, here's a MAC address. What's a link local address be? Just because people are mean and that's what they do, right? So let's just put that into one bucket. The main reason it's important is not because this auto-generated address is really going to be useful. It's not, because we really use the global address for most everything. The main thing that you'll start seeing is that routing protocols, when you get there, I'm giving you a foreshadow of what's to come. When you get to routing protocols later on, you will find that they use their link local address to form neighbor relationships because it's considered the more stable address. So rather than having the global address, which could be all over the place, when routers form neighbor relationships to exchange routes, they'll use that auto-generated address to do so. So that's why it's useful to know what this link local address at least is. Knowing how it's generated, I would say that's probably, if you're studying for an exam and somebody just wanted to be mean and test you on it, that would be a great mean question. So you've now seen the 5 types of IPv6 addresses and how they're used. I hope this has been informative for you, and I'd like to thank you for viewing.